Ladies and gentlemen, let me welcome you to the 7th session in this series. In this video, we will see the classification of signals. So the contents of today's session are your learning outcomes, then the classification of signals. In the beginning, we have seen the broad classification of signals into discrete time and continuous time signals. Now we see further classifications like energy signals and power signals, deterministic versus stochastic signals, or random signals, periodic versus non-periodic signals, causal versus non-causal signals, even versus odd signals, and then the summary of understanding. So your learning outcomes are you will define and compute the energy and power of various signals, both discrete time and continuous time. You will learn to compute the energy of a continuous time signal, energy of a discrete time signal, energy of a power signal, both discrete and continuous. The power of a discrete time signal, the power of a continuous time signal. Then you will learn the various classifications of discrete and continuous signals. Now, besides the classification, in the broad classification into continuous time signals and discrete time signals, there are further classifications like energy signals versus power signals, deterministic versus random or stochastic signals, periodic versus non-periodic signal, causal versus non-causal signals, even versus odd signals. Now, what is the energy of based on the energy of a signal, value of the energy of a signal, you can have a classification like energy signal. That is, if the energy of a signal is finite, then it is called an energy signal. That is, if a signal has got finite energy, then it is an energy signal. That is, what is the energy of a signal? Suppose let us look at a continuous time signal xt. What is the energy of this signal? This energy E, that is an integral from minus infinity to plus infinity, mod xt square dt. So I take mod xt square, the integrate over all possible times, that is from minus infinity to plus infinity. And if this value E is finite or less than infinity, then this is an energy signal. Now, what is the energy of a discrete time signal xn? Here the time axis is discrete, so instead of xt I have xn. So instead of mod xt square I have mod xn square. Since mod xn square values are discrete, instead of the continuous integration I have a discrete summation, that is n from minus infinity to plus infinity mod xn square. That is the energy of a discrete time signal. Now let us compute the energy of a continuous time signal xt equal to a e raised to minus alpha t minus at ut. This is a right-sided signal due to the presence of this ut, because ut is 1 for t greater than 0, for t less than 0 it is 0. So this is an exponentially decaying signal starting with a to 0. This is an exponentially decaying signal in the interval 0 to infinity. So here if this a is positive, what is the energy of the signal? That is minus infinity to infinity mod xt square dt. So due to the presence of this ut, the integral is modified as integral from 0 to infinity. A square of this is a square, though, so a square being a constant, it comes out of the integration, and e raised to minus alpha t square becomes e raised to minus 2 alpha t dt. So on integration, it becomes e raised to minus 2 alpha t by 2a, and that small 2a comes out a square by 2 small a. This integration limit reverses due to the presence of the minus sign. So it is the upper limit is e raised to 0, that's a 1, and the lower limit will be e raised to minus infinity. So it is this integral default integral becomes 1, and so it becomes a square by 2a. This is a finite value. So this signal a e raised to minus alpha t, the exponentially decaying signal, this is an energy signal. With a greater than 0, the energy is finite. So now let us consider a discrete case, like I have a discrete power signal as a raised to n un. So xn is a raised to n un. Due to the presence of this un, it is a right-sided sequence. This a raised to n from 0 to infinity. So with the magnitude of a between 0 and 1, what is the energy of the signal? That is from minus infinity to plus infinity mod xn square. So it is from due to the presence of this un function, this summation becomes summation is modified from 0 to infinity. So it is 0 to infinity a raised to 2n. So a raised to n, the square of a raised to n is a raised to 2n. So that this geometric series by binomial theorem, it is 1 by 1 minus a square. So if this magnitude of a is greater than 1, then this sequence will not converge. So 1 plus a square plus a raised to 4 does not converge. So then it is not an analogy signal. So this is an analogy signal. This a raised to n un is an analogy signal for values of a between 0 and 1. Now consider another continuous time signal, a pulse signal, that is 1 from 0 to tau, that is ut minus ut minus tau. So this value, this pulse is high, or 1 from 0 to tau time. So this is ut minus tau. So everywhere else it is 1 from 0 to tau, everywhere else it is a 0. So the energy of the signal is is integral 0 to t 1 dt, so it becomes a tau. This is less than infinity, so this is also an energy signal. So this pulse signal is an energy signal. Let us consider the discrete equivalent of this, say p of n, that is un minus u n minus m. It's a discrete case of this. So its energy will be E is from 0 to n minus 1. That is, this signal is 1 from 0 to m minus 1. So this is 0 to m minus 1, 1. That is m. That is less than infinity. So this is also an energy signal. Now, what is the power of the signal? Suppose if you encounter periodic signals, etc., they are mostly power signals. You tend to compute the power of that signal. So what is the power of this signal? So what I can do is I compute the energy over one period. So take a periodic signal, take one period, over one period you compute the energy of the signal, that is from minus t by 2 to t by 2 mod xt square dt. Then I average over one period, that is 1 by t. Then so this is the energy per period. So then the power in the signal is, I apply the limit t tending to infinity, so that the whole span of the signal is covered. So P is a limit t tending to infinity, or limit t tending to infinity 1 by t minus t by 2 to t by 2 mod xt square dt. Understand it this way. Mod xt square is actually the energy of the signal. I compute over one period, that is from minus t by 2 t by 2 mod xt square. It is energy per period. Then I average over one period 1 by t. Then I apply the limit t tending to infinity to encompass the whole of the signal, and the resulting thing is the power in the signal. Mostly these periodic signals, etc., are power signals. Infinite duration signals are sometimes power signals, but we cannot generalize that. If you look at an exponentially decaying signal, it is infinite duration, but it is an energy signal. So one cannot easily generalize, but generally speaking, periodic signals, etc., are power signals, while finite duration signals and sequences are energy signals. Now let us consider a periodic signal xt equal to a cos 2 pi fct. This is a continuous time cosinusoid. It has a period of tc, that is 1 by fc, and the power in the signal is p is over one period I compute the energy of the signal, that is from 0 to tc mod xt square dt. Then I average over one period, that is 1 by tc multiplied by 1 by tc. Then I apply the limit tc tending to infinity. So what is mod xt square? It is a square cos square 2 pi fct. So this becomes an a square comes out. It is a limit tc tending to infinity, a square by tc, 0 to tc cos square 2 pi fct dt. Now this is of the form cos square theta, which is nothing but 1 plus cos 2 theta by 2. So that divided by 2, it becomes a square by 2c, 0 to tc, 1 plus cos 4 pi fct. How did I write that? I use the identity. Cos square theta is 1 plus cos 2 theta by 2. So here the first term on integration, it becomes t, and this term on integration, this cosine term on integration becomes sine 4 pi fct by 4 pi fc. I apply the limit from 0 to tc. What happens is, the first thing, t, on application of the limit from 0 to tc, it becomes a capital Tc, and the sinusoidal function integrated over, when I apply the limit from 0 to tc, it becomes a 0. and this becomes a square by 2c into tc, it becomes a square by 2. This is a well established result, probably you all know that. The power in a cosinusoid is a square by 2. Now, let us look at the power of a discrete periodic signal. What we have seen is the power in a continuous time signal, periodic signal. Now, let us see the power in a discrete periodic signal, that is xn equal to xn plus n, where n is a fundamental period. Now, what is the power of the signal? I compute the energy over one period, say mod xn square. Instead of the integration, I have a discrete summation because I am dealing with the discrete values. So the summation limit is from minus n to n. So the total period is 2n plus 1 because the origin is also there. So I have a total span of 2n plus 1. I average over that period 1 by 2n plus 1 limit. Then I apply the limit n tending to infinity to encompass the total spread of the signal. So P is equal to limit n tending to infinity 1 by 2n plus 1 summation minus n to n mod xn square. Now let us consider a unit step sequence un. What is the power of that signal? It is a power signal. So what is the power of that signal? That is over 1 by 2n plus 1, you compute the power in the un. So un everywhere the value is a 1, that is from 0 to infinity the value is a 1. So the sequence, the summation, instead of minus n to n, it becomes a 0 to n mod 1 square. So it is actually n plus 1 by 2n plus 1. When I apply the limit n tending to infinity, if I make a division by n, it becomes 1 plus 1 by n by 2 plus 1 by n. So this becomes a 1 by 2, which is finite. So it's a power signal. The unit step sequence un is a power signal with the power half. Now this what we have seen is a classification energy signals and power signals. That is, if the signal has finite energy, it's an energy signal. If it has finite power, it's a power signal. Mostly the continuous, mostly the periodic type signals, and most of the signals that extends to infinity, that is infinite in duration, they are mostly power signals. And most of the finite duration signals like rectangular pulses, etc., or triangular pulse, etc., they are all energy signals. And sometimes infinite duration signals like exponentially decaying signals, decaying power signals, they are also energy signals. Okay. Now we see another kind of classification, the deterministic versus random or stochastic signal. So any signal that can be uniquely described by an explicit mathematical expression, you know the value everywhere, like a table of data or a well-defined rule, then is there behind a signal, then it's a deterministic signal. You know the value everywhere. There is no ambiguity, there is no randomness about the signal. It is called a deterministic signal. Rarely such a signal comes by. Most of the signals have some kind of ambiguity, some kind of randomness in it. When we say deterministic, we know everything. The past, the present, future values of the signal are known without any uncertainty. But in reality, there is always some kind of uncertainty associated with signals because there is some kind of measurement or some kind of noise everywhere. So most of these signals are random in nature, or random, or more rigorous word is stochastic. Most of the signals are stochastic in nature. Then we see another classification, that is a periodic versus non-periodic signal. Some of you may be familiar with this. Suppose I have a continuous time signal xt. If it is periodic, if xt is t plus or minus t for the fundamental period t. It can be xt equal to xt plus t capital T, or it can be xt minus capital T, or it can be xt plus or minus mt, anything, where m is an integer. So xt is xt plus t for a fundamental period t. Suppose you look at the signal, I have the signal xt is a cosine signal a cos 2 pi fct plus theta. This is periodic with the fundamental period 1 by fc. Okay, this is periodic with the fundamental period 1 by fc. After that, it will repeat itself. Suppose I look at the exponentially decaying signal like xt equal to a raised to minus alpha t ut. This is a non-periodic signal. This is an exponentially decaying signal. You won't see any periodicity in it. It's a non-periodic signal. And when it comes to a discrete case, a discrete signal xn is periodic if xn is xn plus capital N for some fundamental period capital N. It can be either xn plus or minus n, or it can be xn equal to xn plus or minus some small m into n, where m is an integer. It can be any way. So for some fundamental period, if the signal repeats itself, then the signal is periodic. Suppose if I have a signal like a cos 2 pi fc n plus theta, this is a periodic signal. You know that is a cosine function. It's periodic with the fundamental period n is 1 by fc. Okay, n is equal to 1 by fc. That will be the fundamental period of the signal. So A or fc is how many? This has a fundamental period 1 by fc. And the signal xn equal to a e raised to minus alpha n u, and this is non-periodic because this is an exponentially decaying signal. This is a non-periodic signal. Now we see another classification, the causal versus non-causal signals. So suppose a continuous time signal xt is fully right-sided, like it is causal if xt is 0 for t less than 0. If all values of x are 0 for t less than 0, then it's a causal signal. Say, look at the signal ut, xt equal to ut. This is a causal signal because ut is 0 for t less than 0. While ut plus 5 is not, because it has some values from minus 5 to 0 values are there. So it is not a causal signal. And likewise, a discrete signal xn is causal if xn is 0 for n less than 0. If all values of the function are 0 for n less than 0, then it is causal. See, the signal xn is equal to un is causal, while xn equal to un plus 5 is not causal, because from minus 5 to 0 the values are there. So xn equal to un plus 5 is not a causal signal. Now then there is a classification even versus odd signals. There is a continuous time signal xt is even if xt is equal to x minus t, and odd if xt equal to minus x minus t. That is, if it has got mirror symmetry about the origin, about the y-axis at origin, if it has got symmetry about the y-axis at origin, then it is an even signal. If it has anti-symmetry, then it's an odd signal. That is, if xt equal to x minus t, if the flipped function is the same as the original function, then it's an even signal. If it is not, if it's a negative one, then if you see an anti-symmetry, then it's an odd signal. Look at this signal a cos 2 pi fct is even because it is a cosine function has mirror symmetry at t equal to 0 about the y-axis, while xt equal to a sine 2 pi fc, this has anti-symmetry, so this is an odd signal. Okay. Likewise, for the discrete case, a discrete signal xn is even if xn is x minus n, and odd if xn is minus x minus n. Okay, if at n equal to 0, I have mirror symmetry about the y-axis, then it's an even signal. If I have anti-symmetry, then it's an odd signal. A cos 2 pi fcn is even, while xn is a sine 2 pi fcn is an odd signal. Now coming to the end, summary of understanding. Here in this video you defined and computed the energy and power of both discrete time and continuous time signals. So we have seen the broad classification, energy signals and power signals. If the energy of a signal is finite, then it's an energy signal. If the power is finite, it's a power signal. So we have seen that most of the periodic signals, etc., are power signals, while finite duration signals and exponentially decaying signals, they are all energy signals. So we have seen, you have seen further classifications like the deterministic versus stochastic signals, even signals versus odd signal, causal versus non-causal signals, etc. So with this, we come to the end of this session. Thank you all.